Hello everyone, this is your course instructor Harshita, working as an assistant professor in the Department of Electronics and Communication, Sai Vidya Institute of Technology. In this session, we will be studying about binary cyclic codes under the module 4. So before proceeding, we need to understand what these binary cyclic codes are. So the binary cyclic codes are a subclass of linear block codes which we have studied earlier. And these codes will have an algebraic structure or a mathematical structure from which a polynomial representation can be obtained. And with the help of this polynomial representation, we can perform encoding or decoding operation. Coming to the definition of binary cyclic codes. Any linear block code n, k is said to be a cyclic code if every bit right or left cyclic shift of the code is also a code vector of C. For example, let us take a code vector V. So this V is given by V0, V1, V2 and so on till V1, Vn minus 1, which is a code vector of C. Now I'll perform cyclic shift. So we'll get V1 as Vn minus 1. This is shifted cyclically here. So we'll get Vn minus 1, V0, V1, V2 and so on till Vn minus 2. And we'll see that this V1 is also a code vector of C. So we can say n, k linear block code is a binary cyclic code if this property is satisfied. Alright, and this code vector can be represented in the form of polynomial as v of x is equal to v0 plus v1 into x to the power of 1 plus v2 into x to the power of 2 plus v3 into x to the power of 3 and so on till vn minus 1 into x to the power of n minus 1. Okay, you can see that these V0, V1, V2 and so on till Vn minus 1 are the coefficients of this polynomial and they can be either zeros or ones. And these zeros or ones will follow that modulo 2 addition and multiplication rules, and that is given over here. Meaning to say, this is modulo 2 addition of 0 and 1. 0 plus 0 should give me 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Next, this is modulo 2 multiplication. 0 multiplied with 0 is 0. 0 multiplied with 1 or 1 multiplied with 0. Modulo 2 multiplication is 0 and modulo 2 multiplication of 1 and 1 is 1. So this is modulo 2 addition and modulo 2 multiplication, which you're supposed to remember in order to solve problems. Okay, and these code vectors under binary cyclic codes can be represented in non-systematic form and systematic form. First, we'll understand how these code words can be represented in non-systematic form. Non-systematic form, this code word is represented as v of x is given by the product of d of x and g of x, where d of x is the message vector and g of x is the generator polynomial. Okay, and in systematic form, the code words are written as v of x is equal to r of x plus x to the power of n minus k into d of x, where this r of x is the remainder and this d of x is the message and this x to the power of n minus k. You will understand. This will mainly indicate the check bits. You will understand in the upcoming explanation. So basically, this binary cyclic code is represented like this. First will be your message followed by the check bits. For an n comma k linear block code, k will indicate the length of the message. So here message is k bits and length of this code word is n bits. Okay, message including the check bits length is n bits. So if you want only the check bit length, what is that? N minus k. So check bit's length is n minus k. So here k will indicate the message bits and n minus k will indicate the check bits. N bits is the length of the complete linear block code. Alright. And this code vector is represented in the systematic form as like this. See here. First will be the remainder that is indicated by the parity check bits. Next we'll have the message. Okay, so these messages are k bits of length and they're indicated by d0, d1, d2 and so on till dk minus 1, and these parity check bits are represented by the remainder r0, r1, r2 and so on till rn minus k minus 1. So what is this remainder? How did we get that? I'll explain it. So this remainder polynomial, that is parity check polynomial, r of x is written as r0 plus r1 into x plus r2 into x square and so on till rn minus k minus 1 into x to the power of n minus k minus 1. So how did we get this remainder? I'll explain you now. The parity check matrix is the remainder obtained by dividing x to the power of n minus k into d to the power of d of x by the g of x. This g of x is nothing but the generator polynomial. Alright. So this x to the power of n minus k into d of x is divided by g of x. As you can see here, we'll write it like this, where g of x is the divider and x to the power of n minus k into d of x is the dividend, and upon performing the division operation we'll get the remainder as r of x, which is nothing but parity check matrix, and q of x is the quotient that we obtain. Now from this division operation, can we write x to the power of n minus k into d of x as equal to q of x into g of x plus r of x? Yes, we can absolutely write. So we'll write that equation and highlight this equation. You will have to remember this equation. So this q of x is nothing but the quotient and this r of x is nothing but the remainder, and g of x is the generator polynomial, which is the divisor, and this x to the power of n minus k into message vector. Okay, and this v is nothing but the code vector. Now we'll write the polynomial for this code vector. We'll write it in form of a polynomial. So we'll get v of x is equal to, in systematic form, this code vector is written as remainder plus x to the power of n minus k into d of x, where n is the length of the code word and k is the length of the message. Alright, so this is the systematic representation of the code word. So now let's take up an example in order to understand the representation of the polynomial in systematic and non-systematic form. So this is the question. The generator polynomial of a 7,4 cyclic code is g of x equal to 1 plus x to the power of 3. Find the 16 code words of this code in the following ways. First sub question is, by forming the code polynomials using v of x equal to d of x into g of x, where d of x is the message polynomial. Second sub question is by using the systematic form. So in the question, we are given with a 7, 4 cyclic code, meaning to say n is equal to 7 and k is equal to 4. And the generator polynomial is given as 1 plus x cube. From this data, we are supposed to find 16 code words by representing the code words in both non-systematic form and systematic form. In non-systematic form, we should use v of x is equal to d of x into g of x. Okay, so first we'll solve the first sub question. So let us consider the message vector. Here we have 7, 4, isn't it? So the message vector will be of length 4. So we'll consider a message vector, say 1010. So this message vector is represented as D0, D1, D2 and D3. So that is, we have taken it as 1010. Okay, so this first bit will represent x to the power of 0, second bit will represent x to the power of 1, third bit will represent x to the power of 2, fourth bit will represent x to the power of 3. The message polynomial we should write from this message vector. So message polynomial is d of x, that is given by, for x to the power of 0 I have 1, so I'll write x to the power of 0, that is nothing but 1, so I'll straight away write 1. Next, x to the power of 1 into 0, that is 0. Next I have x to the power of 2 into 1, so I'll write x to the power of 2. And for x to the power of 3 I have 0, so that is 0. So d of x, that is message polynomial, is nothing but 1 plus x square. So the code polynomial, that is v of x, is nothing but, see here, d of x into g of x. D of x we have already found out here, and g of x is given in the problem itself as 1 plus x cube. So now what we are supposed to do, v of x is equal to d of x into g of x. So substitute d of x and g of x and multiply both the polynomials, so we'll get this expression 1 plus x square plus x cube plus 5. So wherever you are performing addition or subtraction or multiplication, you will have to follow modulo 2 addition or multiplication or subtraction. So here we have addition, so perform modulo 2 addition of x to the power of 3 plus x to the power of 3. Here you can see when I take x cube as common, I'll get 1 plus 1. So 1 plus 1 is nothing but 0. When you go back to this notes, you can see 1 plus 1 is 0. So I'll write 1 plus 1 as 0. So you will get 0 into x to the power of 3, that is nothing but 0. So these two terms are 0. The only thing that is remaining is v of x is equal to 1 plus x square plus x to the power of 5. So I'll write the code vector from this polynomial. So the first bit is nothing but x to the power of 0. So I have that. So I'll write 1. Next x to the power of 1 I have. So I'll write 1 again. X to the power of 2 also I have. So I'll write 1. X to the power of 3 I don't have, so I'll write 0. X to the power of 4 also is not there, so I'll write 0. X to the power of 5 is there, so I'll write 1. Since this is a 7, 4 cyclic code, so the code length also should be 7. So here we have written only 6 bits from this polynomial. So I should write one more. That is, I'll go for x to the power of 6, which is not there. So I'll write 0 again. So the code vector for the message 1010 is 11100 and 10. So in this way, we will consider all the messages, that is 0000, 0001, 0010, and so on till 1111, and calculate the code vectors by performing multiplication of message polynomial and the generator polynomial given in the data, and we will find out the code vector as we found it out now. So I want all of you to consider all these messages and find out the code vectors, and I want you to cross verify whether you are getting these code vectors correctly. And next, this is about the first sub question. Next, what are we supposed to do? We are supposed to find the 16 code words of this code by using the systematic form. So how will we do that? In systematic form, we are already given with n comma k cyclic code, that is 7 comma 4, n is equal to 7 and k is equal to 4, and n minus k is nothing but 7 minus 4, that is 3. So in cyclic codes, first we'll write the check bits, next we'll write the message bit. Check bits is of this length, that is 3. So first 3 bits will be check bits, and the last 4 bits, that is k equal to 4 bits will be the message bits. So first we need to find the check bits. So how will we find the check bits? Students, please remember, check bits are found by division of x to the power of n minus k into d of x by the generator polynomial, that is g of x. Alright, so we should remember this. X to the power of n minus k into d of x by g of x is equal to the sum of quotient and the remainder, that is q of x plus r of x. Now for this we will consider the data or the message to be 1, 1, 1 and 0. And from this we can write a message polynomial, that is d of x, as this is x to the power of 0, that is nothing but 1. Next I have x to the power of 1, so I'll write x. Next I have x to the power of 2, so I'll write x to the power of 2. Here I have x to the power of 3, but here I have 0, so I will not write x to the power of 3. So the message polynomial is 1 plus x square. Now I want to find out this product term, that is x to the power of n minus k into d of x first. So x to the power of n minus k is 7 minus 4, that is nothing but 3, right? X to the power of 3 into d of x is 1 plus x square, right? So performing the multiplication operation for x cube into d of x, we will get x cube plus x to the power of 4 plus x to the power of 5. And now we'll perform the division operation. So we'll write the generator polynomial over here, x cube plus x plus 1, and the d of x into x to the power of n minus k. I'll write it here in the order of decreasing powers. Okay, so x to the power of 5 plus x to the power of 4 plus x to the power of 3. G of x also you're supposed to write it in the similar way. You will have performed polynomial division in your lower semesters, so I hope all of you know this. So first we have x to the power of 5 term over here. In this divisor term we have x to the power of 3, so I will have to multiply it with x to the power of 2 in order to get this x to the power of 5 term. So I'll write x to the power of 2 over here. So x to the power of 3 into x to the power of 2 is x to the power of 5 plus x into x to the power of 2 is x to the power of 3 plus 1 into x square is x square. Now we will have to perform modulo 2 subtraction. So these two terms will get cancelled, and now we will have to consider the terms with even powers. So here I'll consider x to the power of 4, and here I'll consider x to the power of 2. And next here I have x to the power of 3. Here I have x to the power of 4. So I'll have to multiply it with x. So x to the power of 3 into x is x to the power of 4 plus x into x is x to the power of 2 plus 1 into x is x. So these two terms will get cancelled and the remaining term is only x. So this is nothing but the remainder. So the remainder polynomial is r of x equal to x. So this x to the power of 0. So I will have to write the code from this polynomial. X to the power of 0 I don't have, so I'll write 0 first. Next, x to the power of 1 I have, so I'll write 1. Remember, go back to the explanation. What did we write first? N minus k is the check bits length. So what did we get n minus k as? 3. So first 3 bits will be check bits. So from this x, we need to write a 3-bit code word. So x to the power of 0 I don't have, so I'll write 0. X to the power of 1 I have, so I'll write 1. X to the power of 2 I don't have, so I'll write 0. So the code word for x is 0, 1, 0. And next is nothing but the data that we have considered, that is 1, 1, 1 and 0. So I'll write 1, 1, 1 and 0. So the code word in systematic form for the data 1, 1, 1 and 0 is 0, 1, 0, 1, 1, 1, 0. You can see this is also a 7-bit code word. So like this, we will have to write the code words considering all these messages, that is 0000, 0001, 0010 and so on till 1111, and we will have to perform the multiplication of x to the power of n minus k with the d of x that is given over here, and we will have to divide this by the generated polynomial that is given in the question, and by using this remainder polynomial you will have to write the code word first and then followed by the data. We'll get the code vector in the systematic form. So I want all of you to consider all these 16 messages and find out the code vectors for all the respective messages and cross verify whether you are getting these code words or not. In case of any difficulty in calculation or any doubts, you can always contact me. I'll clear them. So this is about this session. We'll wind up the session now. In the next session, we'll continue with the module 4. Thank you all.